Now that we've concluded our discussion of first-order differential equations, we're going to start talking about second-order differential equations. But as a precursor to that discussion, I want to talk about something called linearity. This is, as you may have guessed it, this is a property of linear differential equations. So, linear differential equations. And it is super important to the coming topics because after first-order differential equations, we mainly start to only focus on linear higher-order differential equations for the most part because they have really nice defined ways to solve them. And all of the methods for solving linear differential equations of order higher than 1 start to stem from this property of linearity. So it's super important. Now, with all of the rambling aside, what is linearity? Well, let's see if we can write out a second-order differential equation that is linear in its most general form. Maybe we have some function f1 of x getting multiplied into the second derivative of y, plus some other function of x, just arbitrary, times the first derivative, plus a third function of x times y equaling a fourth function of x. Now, in general, you could also divide by f1 and then get 3 new functions of x that are different. That's fine, but for now, we'll just keep it even more general than the general form, which is just a joke, of course, because this is just as general as if you didn't have the f1. All right, that aside, this is the most general form of a linear second-order differential equation, because you have any function of f in each of these slots. So, if we call this left-hand side, because the right-hand side is actually unimportant to our discussion today, so we can just get rid of it. If we call this left-hand side, this is our differential equation. We can almost imagine it as some kind of a function that takes in a function and then spits out a new function. Let's call that operator in a way, s. S takes in a function, and then what it does is it spits out f1 of x times the second derivative of that function, plus f2 of x times the first derivative, plus f3 of x times the function itself. So, just as a brief example, if we had the second order differential equation that was y double prime plus 3y prime plus xy, then this would be the s function, and if we plugged in to this s of, say, s of this sine of x, what we would get would be the second derivative of the sine of x, which is the negative sine of x, plus 3 times the first derivative of the sine of x, which is the cosine of x, plus x times sine of x itself. So in this case, for this differential equation, s being the second derivative plus 3 times the first derivative plus x times the function itself, if we plug in the function sine of x, we would get second derivative, negative sine of x, plus 3 times the first derivative, which is the cosine of x, plus x times the function itself, x sine of x. So I hope now it's a little bit more clear what it means to have a function that can take in a function and spit out a new function. Because this is, we can maybe even call it an operator that takes in a function and spits out a new function. All right, with that aside, let's, I guess, yeah, okay. Let's actually keep that around just so you can keep it around if you want to look at it. So, now we have this most general form of second-order linear differential equations. Now let's start to talk about linearity. Linearity is something you may already be somewhat familiar with from the idea of a straight line. What it says is, in its most general form, if you have something like big H, and big H takes in two things, A and B, takes in A plus B, and it does something to them. Linearity has two properties. It says if you say, if H is to be linear, then H of A plus B must equal H of A plus H of B. And not only this, it must also be true that if we took h times some constant times, and I was going to call it a, but let's call it c just to be clear. It doesn't have to be the same thing. H of some constant times a new thing, c, that this is just going to be that constant, k, times h of that thing, c. These two properties here imply linearity, and linearity implies those two properties. So it goes both ways. And what do these properties mean? Well, we can say in a sense that the function h acts the same over the whole spectrum of whatever the a's and b's are. Like if you imagined that we had a graph here of a line, I mean, as its namesake, definitely satisfies linearity. So let's say we had a line here, and this is x-axis, y-axis. If we were to take some kind of a point at, let's say, x equals 1 and x equals 2, and add them, you would notice that if you took the corresponding y values at x equals 1 and x equals 2, that is the same as if you added them to get to x equals 3. This is the same as, so this y value is the same as just taking this y value and adding that y at 1. Anyway, so that's the same. If you scaled it, it's the same as just scaling your y value difference. So hopefully for lines, linearity makes a bit of sense. What it means here is that you have this. And more specifically, we can extend these, not extend, we can consolidate these two conditions into a single condition, which is that h of some constant times something, so k1 times a, plus some other constant, k2, times b, this has to equal k1 times h of a plus k2 times h of b. This also, both ways, linearity implies this, and this implies linearity. So this is the property that we'll be working with for what linearity is. And what we're going to do, briefly, is show that any linear differential equation satisfies linearity. So that they actually are linear, and they satisfy this property. And the reason is because as we start to talk about second-order differential equations, this property of linearity is going to show up time and time again. It will be one of our most useful tools in solving them. Okay, so with all that said, let's get proving. So we can actually keep generality. So without loss of generality, we can say y double prime with no function, a constant of 1 attached, because if we did have some constant like 4, we could divide it through into our other arbitrary functions. So we have y double prime plus f1 y prime plus f2 y double prime equals, wait, what am I doing? That's not y double prime, that's just regular y, sorry, equals f3. But for now, let's not even worry about the equals. Let's just say that this equals when you apply the s operator to a function y. Alright, now what we want to prove to show that linearity is holding is that s of some constant, k1, times some function y1, plus a different constant times a different function, k2 and y2, that this is precisely equal to k1 times just applying the function to y plus k2 times just applying the function to y2. If we can prove this, we prove linearity. So let's see what we can do to prove this. We have our differential equation up here. Let's just plug in, instead of y at every point, let's plug in k1 y1 plus k2 y2. And what are we going to get? We are going to get k1 y1 plus k2 y2 double prime plus, and now we have our first arbitrary function f1 times k1 y1 plus k2 y2, same thing, but now only the first derivative, plus another arbitrary function times the same thing, k1 y1 plus k2 y2. And this is going to be the same as, we know that the differentiation operator at least is linear, and this is a property that many calculus students are very familiar with, but they don't have the formal word linearity to describe it. But if you had, let's say, two functions, f and g, if you said f plus g prime, everyone knows that this is the same as f prime plus g prime. And if you have some constant c times your function f, you take the derivative of this. This is the same as c times your function f derivative. So intuitively, we know that the differentiation operator is linear. So we can apply that here. We have k1 y1 plus k2 y2 second derivative. We can split it apart as k1 times the second derivative of y1 plus k2 times the second derivative of y2. And I'm actually going to start color coding things so that we see what's going to happen. Plus k2 times y2 double prime. And now we're going to say plus f1 k1 y1 prime. And again, the reason I'm not doing primes on the k1 is because the constant, you just factor it out. And then here we have plus the same f1 times k2 times y2 prime. And now we do plus f2 times k1 y1 and plus f2 times k2 y2. And I hope that my color coding has made this more clear. We have 3 terms in blue, 3 terms in green. And what's the difference? Green has y2 and blue has y1. If we simply group the terms, what we arrive at is that this, which remember that this equaled s of k1 y1 plus k2 y2, that this grouping the blue is k1 y1 double prime plus k1 y1 prime times f of 1, so f1 k1 y1 prime plus f2 k1 y1. It's a lot of subscripts, I know, but roll with it because we're about to finish. Now we say this is the same as k2 y2 double prime plus that first function times k2 y2 first derivative plus f2 k2 y2 with no derivatives. And this is the key, because now it is pretty easy to see, I hope, that this right here, this is the same as s of just y1, because we have k y1 double prime plus f and then k2 y1 prime, and I suppose I should say this is k1 times s of y1. And then this right here is k2 times s of y. Because again, what we can do now is we can say for each of these, we have a k1 on each of them. So we can factor out the k1 here. And here, we have a k2, so we can factor out the k2. And I guess I'll move this plus sign around so I have more space. Plus k2 times this. And here, what we have is, and I guess I'll rewrite it to make it very clear, is that we have k is equals k1 times y1 double prime plus f1 y1 prime plus f2 y1. And here we have plus k2 times y2 double prime plus f1 y2 prime plus f2 times regular y. Here we have k1 times what sy1 is, which is the second derivative plus an arbitrary function times the first derivative plus another arbitrary function times the function itself. And then we have k2 times the exact same thing for y2. So what we've shown is that because really of the linearity of the derivative, because of that property, what we've shown is that if you have any arbitrary second order differential equation, which you name as s of some function y, that this exhibits the property that s of some constant times a first function plus some second constant times the second function, that this is indeed equal to that first constant times your operator on just the first function, plus that second constant times your operator on the second function. And again, this is just all really falling out of the fact that the derivative, you can do these things, because once you can do these things with the derivative, all you need to do is actually do it and then rearrange it. So because we've proved this, we've also proved that the second order linear differential equation, really any linear differential equation, if you think about how you could extend this method, that this is linear, that it implies linearity. And now that we have this property of differential equations, that we can split them apart like this, and also you can think about maybe reconstructing, this is going to be immensely useful as we commence our discussion of how to actually begin to solve second order linear differential equations. I'll see you then.